Hello everyone, my name is Gabor Mészáros and this is Genomics Bootcamp, where we speak about genomics from the beginner's perspective. Today we will speak about single nucleotide polymorphisms, or SNPs as they are called in a shorter form. Now the SNP data is the data type that is most spoken about in the channel, so it is rather important to know what it is. So if you are not quite sure what actually SNP data is and how it looks like from the theoretical perspective, as well as how it looks like in the data files, then this is the video to check out. So just proceed and see what is it about.
Here is a presentation I put together for you about the single nucleotide polymorphisms, first from the theoretical perspective and then later on showing some of the practicalities, how they actually look like in the data files. So single nucleotide polymorphisms, or SNPs in short, are point mutations or single base substitutions occurring on the genome. As you see in the picture, so if you compare two individuals, really, what you will see that most of their genome is exactly the same, and they differ at certain places. So these certain places are called variants, and one of the forms of these variants are single base substitutions or single nucleotide polymorphisms, or SNPs. As you see it in a picture, so there is just one spot where they differ. In reality, however, there is not just one SNP when you compare any two individuals, but there are literally millions of them. These SNPs are then used as genomic markers throughout the genome. Now, the characteristic of the genomic marker is that we know its position, so where it is located exactly on the genome, and we know its genotype, so we can associate it with the further traits of interest, or we can use them when we are searching for underlying genes. So I know that this concept might be a bit distant, but let me give you an example. And the example is called, where's the party at? I mean, yeah, so this particular example I use on my lectures, but it's not from me, but unfortunately I forgot the source where I've heard it from somebody, but unfortunately I cannot remember who it was exactly. But anyway, so the concept is the following. Your goal is to find a party that is taking place in a house somewhere. Now, this is a crude depiction of the house, and the houses tend to be on the streets. So these are the various houses, and you have the road and everything. So the party is somewhere here, but the party is in a town where you haven't been before, and the street where the house is located is very long. I mean, very, very long. Now you are in a new city looking for a party on a very long street. And what you don't want to do is go into each and every house and knock on the door to see if there is the event happening there. Fortunately, you know a few people in this street, and well, you know also their phone numbers. You're quite certain that these people are not at the party that you are going for, but still they can give you some information. So you call your first friend and ask if they hear music playing in their neighborhood. And well, they just say, well, sorry, there is all quiet here. Then you call another friend and ask the same question. Do you hear music in one of your neighbors or around you? And they say, well, there is some music around here, but it's not very strong. And then you call your third friend, and you cannot even speak with them very much because you hear that there is just an awful lot of noise and music playing all around them. So you are quite certain that the party must be somewhere there. So even if you don't know exactly where the party is, so you know the address of your friend, you go to their address, and then from there you can find the party easily. Now, if we relate this example to the genomics, so the street is actually the whole genome, and the houses or yeah, where your potential friends are located are the SNPs. So the same way, you know the addresses and locations of the SNPs, and if they give you some indication that something is happening there, then you could be seeing some kind of a signal, and these signals then indicate you that somewhere there are the underlying genes of interest that you are looking for. Millions of now we have millions of SNPs in any two genomes, but if you're interested in a genotyping of these SNPs, then you mostly go for the so-called SNP chips that are, well, also called as microarrays or bead arrays. So on the left side, there is a picture of such a SNP from Illumina, but well, this is one of the companies, one of the manufacturers. There are also others which make these chips, which you can then use for genotyping. Now, I don't want to get too much into detail right now about the genotyping process. I might make a video on this afterwards. At least there are some interesting details that could be useful to know. But for now, just I want to mention that the SNPs on these SNP chips are biallelic by design. This means that they have exactly 2 alleles that translate to 3 genotypes. Also, the SNPs can be missing. So as I mentioned here, so the alleles, for example, there is a allele A and B, then genotypes could be either AA, so it's homozygous, AB heterozygous, or BB, other homozygous. Now, the whole process of genotyping when it comes to practice is that, well, you get some DNA samples. These could be, well, from various sources, blood or tissue or semen or hair follicles or anything like that. Then there is a lab work associated, well, DNA extraction lab work, where you can basically make a contract with a company that does all this for you. So basically you don't need to have a laboratory or a genotyping machine to get SNP data. But at some point they can deliver you the actual data, which you can then use for your analysis and hopefully get some nice results. Now the genotype data looks like this. I will not go into details right now. I made a video on this, so I will link it into this to this video, and hopefully at the end product of this this video there you will see a link on the top right corner. So anyway, the genotype files at the end are just some huge text files. But the important thing is, maybe I just point it out again, so you know their genotype that is located in the, let's say in this particular example, in the PET files, and they know their address, so they know which chromosome they are at, and also their exact nucleotide position. So much like in the where is the party at example. So you knew the address of the friend where you went to find the party. Here you know the address of each of the SNPs on the genome. Now, when it comes to practicalities in terms of genotype or allele coding, there are various options. So this slide will list these options, and later on, or just right after that, I will show you also actual text files on my computer. This so-called nucleotide coding is one of the most common ones. Here, what you see are actually the 4 nucleotides, G, C, A, and T, that are kind of, well, they appear on the DNA. So you can actually see the exact nucleotides in the files that are delivered from you, either from the genotyping machine or well, basically from the genotyping lab or company. Now you see that, so is it brackets here, there's a top, which is just to highlight that, so there is an additional, frankly, complication in here, because when the genotyping is done, then the so-called final reports are generated, and there are two strands that are being delivered to you. One is called top and other one is called forward. Both of these are nucleotide coding, so both of these would have the same allele codes, but if you compare them, they are not exactly the same genotypes. So this poses significant risks when you want to merge data from various sources. Again, I don't want to get into this right now. I will surely make a video on data merging, and where it will come up as one of the important issues. But I just wanted to point it out here that there are two kinds of nucleotide coding options. Anyway, so then there is a character code. Well, previously it was also a character code, but this is like a so-called AB coding, as you also saw on the slide before. So there is the one nucleotide is coded A, and the other nucleotide in each of the biallelic SNPs is called B. So each of the genotypes are combinations of these two letters. Then sometimes what you have is some kind of programs or software that would require not characters or letters, but numbers. So in this case, what you can also do or can have or receive also from partners or various places are genotypes in a numerical coding, when one of the alleles is coded 1 and the other is coded 2. In Plink, there is also an option that you code the two alleles also with numbers, but these two alleles are 0 and 1. Now, I mentioned to you that on the SNP chips, there are the alleles that are coded, well, could be coded in various ways, as you see here, but then there are also missing values. Now, these missing values have also their specific code. There is a specific letter that shows you that this is actually a missing genotype. And in Plink, this is 0 by default. So if you don't specify anything in terms of code for the missing value, the Plink will assume that the 0 is the missing value. You can, of course, specify anything else when you use a dash missing genotype option in Plink. Of course, well, to know what is the code for the missing genotype, you need to open the genotype file or the PET file or the BIM file and check what it is actually in your data set. If it's 0, it's fine. If it's something else, you need to specify the dash missing genotype. If the coding, of course, is 0, 1, with this part of numeric coding, then this missing genotype is necessary. Otherwise the Plink just gives an error. Then there is also an option to store the data in a genotype format. This is when you denote, for example, the genotype or one homozygous as 0, the heterozygous as 1, and the other homozygous as 2. And then there is an option as well, which is so-called compound genotypes, that is actually allelic coding in Plink, but there is no space between the two alleles for a specific SNP. So it is also kind of a genotype coding, but it's not with the one letter, but with a two-letter format for the genotypes. So with the magic of video editing, we are here in the text pad, and I opened several PET files for you, so you can see also these file formats in practice. First one is, well, almost all of these are from the ADATMap, but I cut it down, so just for one read, so just to, well, basically just to show the contents of the files. The first one is the nucleotide coding. So you see there are these nucleotides here all around. And if you well, we can see that, for example, in here, so there is a missing genotype. Again, I described these files or the PET files in general in one of the earlier videos, so I will not spend too much time on that. But you see nucleotides and the missing genotypes here. Well, maybe one thing to point out: the missing genotypes in the PET files are always two of them together. So if you see one code for the missing genotypes, there should be nearby another one. So at least in the autosomal chromosomes, it should not be that there is just one missing genotype, but both, if there is this genotype is missing, that both alleles are unknown. So you see a missing genotype here, a missing genotype here, and so on. Now, this is the top formatting. The forward formatting looks exactly the same. So actually, you cannot really distinguish if it's just by looking at the data itself, if it's top or forward format. Now, this is the AB format. So this is not a publicly available data. So I just use it as an anonymized form. But you see in the PET file, it is pretty similar as before. So there are the SNPs, there are some homozygous, there are some heterozygous, and there are some other homozygous also missing here are denoted by 0. Next is the numerical coding with this recode 1, 2 in Plink. This is back again with AdaptNav data. You see, it's like the genotypes are now denoted as numbers. And here also, well, the 1, 1 is the homozygous, the 1, 2 is the heterozygous, and the 2, 2 is the other homozygous, and the zeros here are the missing ones. Now I did also recode the 0, 1. One of the alleles is coded 0, and the other one is 1. So that is this format. And here, of course, the missing allele must be changed because that would be then indistinguishable from the one of the alleles, which is a big problem. So I just change it to question marks with this dash output missing genotype option in Plink. So it's fairly easy to do, and yeah, so you can actually assign any character to be missing. Sort of the in-between situation between the genotype and allele coding is the so-called compound genotypes. This you can do such an output file if you want in Plink. Interestingly, in Plink 1.9, if you want to load such a data, you don't need to specify anything. So Plink would recognize that this is in a compound form and load it accordingly. If you want to have an output, such as I did right now with this compound genotypes, you need to just specify dash recode compound genotypes, and you get this. You see there is exactly as before, but there is no space in between the alleles. So basically the combinations of the letters denote the genotypes themselves. And the last thing that comes with this allele coding, sorry, not allele coding, but genotype coding, there are also numbers, but in this case, the numbers mean genotypes. So 0 is 1 homozygous, the 1 is a heterozygous, and 2 is the other homozygous. So there are the three genotypes with a single letter. You also see that the missing ones are here denoted by NA, and there is also a line at the beginning. So this is a very specific file, and you cannot read in such a file in Plink, but you can create such an output file, which is then very easy to load in R, because you see that there is also column names and everything is formatted appropriately. And NA is also the coding style that is recognized in R as missing. So this is already formatted in a way that you can load these genotype files to R with ease.
So that was it about the information about the SNP data, both from the theoretical perspective and also from the practical side, what you can see in the data files when you are doing various genomic analysis. Of course, there is a lot more to tell about SNP data, but I believe this information is enough that you can start. And of course, if you are interested, we can follow up this video with another one with a more detailed information about the SNPs themselves. For now, thank you for your time and have a nice day.